Okay, it's after 2. It's Friday. Um, I say we start. Okay, so the title of what I'm going to talk about today is called Reliability versus Validity in Resting State and Task-Based fMRI. It sounds like a pretty dry topic for a Friday afternoon after lunch. Uh, what I'm going to try to get into in this is something I think is really important about resting state fMRI in particular, but for MRI in general. How do you know you're measuring what you want to be measuring? How do you know you're not measuring something that's totally irrelevant to the things you think you're studying, right? That, for me, that's what is at the core of what we're going to be talking about today. I am, for those of you who don't know me, I'm Steve Gotts. I'm in the Laboratory of Brain and Cognition. I'm the staff scientist in Alex Morton's section on cognitive neuropsychology. Some of the stuff I'm going to be talking about today, Alex is the chief in this section. There are people here who are involved in this work. So we have Adrian and Sarah over here on my right. And Sean, it doesn't look like he's here today. But a lot of people helped us with the topics I'm going to be talking about today. So Vinay in the NMR Center and people in Peter Bandettini's group, Javier and Dan, in particular. Dan is here over there. Okay. So Katie Chong introduced on Wednesday. I don't know if everybody goes to all the lectures or not, but she gave the first talk on resting state fMRI. And so I'm not going to talk a whole lot about the basics of that today, just to give you a really quick contextualization. So, this is a method that in fMRI has exploded. I mean, to say it's exploded, it exploded several years ago. It's even more exploding now. Basically, people lie in the scanner. They stare maybe at a plus sign, maybe they close their eyes. And what the researchers are doing is measuring activity that's ongoing in the brain, spatially throughout the brain. Often people have observed that most of the power in the signal is below 0.1 hertz in that, so it's very slow fluctuation. So if you think about things in terms of actual frequencies of fluctuation, let's say you have 0.01 hertz, that's which is a frequency that has a lot of power there. That's like 100 seconds, okay? So these are very slow cycles of oscillation that are going on in the brain. And so there's been a lot written, a lot reviewed. This is a pretty old review by this point. This is Fox and Rakel, where if you put a seed and you extract a time series, say from this spot in somatosensory cortex, and you can see it's kind of very slow. You can see the seconds here. It's 0 to 300 seconds. You can take that time series and just look at for something like what is the correlation throughout the brain of that signal. And then what you see is you see stuff that's obviously there where you extracted the signal, but also in the supplementary motor cortex as well as in the contralateral hemisphere and other related areas. So people have been using this technique in all sorts of different ways to do things like try to understand the overall system level organization of the brain, to use it in clinical settings where maybe they can't get people to perform tasks very well, and so they want to be able to see if they can notice where there are changes in dynamics between a clinical group and a control group. Okay, so what I'm going to talk about today is the thing that, at least for me, has not had enough attention spent on it. So what is the best way to remove noise in resting state fMRI? So we don't actually have a model of what the actual brain signal that we want to measure looks like in any given context. And even if you knew what it was shaped like, you don't know when it starts. So you have these ongoing fluctuations that are happening pretty much everywhere throughout your brain. And how are we going to find out if the thing we're measuring is the actual neurogenic signal or not? I'm going to go through a number of different things people have tried to do. I'm going to talk about test-retest reliability a little bit. So one idea that Mike Millam in particular, among a number of other people, have tried to push is that, well, we know we want the signals to be reliable because that is a constraint on what we can measure. So, some people have taken that further and tried to use it as a way to figure out what the best way to clean the data is as well. So I'm going to bring up this contrast of validity versus test-retest reliability. And in a particular context, I'm going to show you what happens with regard to those two different kinds of measures and show you how related they are. Okay? So the first thing, though, so I'm sure Katie talked a little bit about this, but why, in task-based fMRI, we had kind of a recipe that does a pretty decent job removing a lot of the artifacts that we want to get rid of. And the analysis formalism using multiple regression and the general linear model, looking at beta weights, it doesn't depend, at least theoretically, on the noise that's in the dependent measure. It's really only on the noise that's in your task variables. So if you know exactly when your task variables are presented, your beta weights in principle really are not supposed to depend on things like head motion and other. Now, if you have artifacts that are correlated with task events, then yes, that can still happen. But if they are unrelated to that, then the beta weight should be a pretty good measure. So people had that context going into this literature and going into this, doing this stuff. And the problem is that for when you're doing tasks, what we were able to do before is we were able to average across trials so that we can get rid of the noise that happens on any given trial. So here's a nice example that I like to bring up. So here's two different subjects. And what I'm showing you here is looking at, for example, individual trials of some given task they're looking at. Versus if we bin them into groups of 4 trials and average them, versus binning them into 9 trials, and so on and so on and so on. And by the time you get to 64 trials, all of a sudden it starts to look pretty nice in terms of the averages. So the more you aggregate, the more stable these responses become, and the easier it is to find things statistically, and so on and so forth. Okay, so in resting state fMRI, we don't have the ability to do that. So there's no moment in time where we can look at some evoked response as easily in order to be able to get rid of noise that way. So anything that causes variation in the measured response will cause fluctuations in the signal, and if it happens across the brain when you're something like you're moving your head, you're going to get it to bleed into the measures that you're using to do your study. Okay, so there are a bunch of different artifacts that we know about that affect. So head motion, you've probably heard discussed quite a lot. There's a whole bunch of research on that. There are also other kinds of artifacts like non-neurophysiological artifacts that come from the heart cycles as well as your breathing and respiration. One in particular we've spent some time looking at is this stuff that's very slow effects of respiration and how that can, when you have a breath withhold, how that can affect the bold signal. There are also hardware instabilities. So maybe the channels in your head coil start to lose conductance and start to go bad sporadically, and that introduces signal that's spatially specific into your volumes. So Kevin Murphy and Rasmus Byrne and Peter have a very nice chapter on this if you're interested in reading more about it. They have a nice summary of all the sort of major classes of noise that we worry about. Okay, so what we really want to do is we want to remove noise in the bold signal, but we don't want to remove the neurally derived part, right? That's really what we want. If we could do that, we'd be good. That's essentially what we'd like to be able to do our science. People use a whole bunch of different ways. In fact, if you go lab to lab, it'll be different, right? I mean, people use different recipes for cleaning their data. They have, based on one thing they saw one time, they have their way they like to do it. And oh, this one study, yeah, you can't use this measure. So, so over time, there's been this proliferation of completely different ways of going about this, and there's really not a unified standard for how to do this cleaning part. So I'm not going to mention too much about ICA today, but some of the results I'll show you will have some ICA involved. So the idea behind using ICA to clean the time series is you're going to decompose your time series into statistically independent spatial components. In fact, what you're trying to do in ICA is find components that are non-Gaussian in space. So when you think about it like that, and you listen to that definition, you realize it's not totally obvious that's going to just cleanly get out the things you want and leave in the stuff you don't want to take out. You can do things like after you've done this decomposition, match to artifact templates in terms of their spatial distribution, and then you can choose automatically to discard certain components or keep them. Some people still do it by hand and eye to eye for individual subjects. In principle, this could work okay, as long as the noise sources are independent of the neurally derived bold components. And the question is, to what extent is that true? And we don't actually have a good answer to that. One thing I will be talking a little bit about today, because we're going to use it in the data we're looking at, is a different variant on this, where we're going to get multiple readouts of the entire brain in each TR. And we're going to do ICA not on the spatial distributions of variance, but on which components seem to behave like the bold signal should across those readouts. So it's a different way of using ICA that is not making the same sets of assumptions that are going on in these other methods. One of the most common ones to do, though, that's a little bit more transparent for everybody who's familiar with regression, and I think that's the reason a lot of people prefer using this, is that it's much more concrete. You can actually look at the signals and understand exactly how it's going, because it's just multiple regression. But what you do is you take a bunch of measures that you think are containing lots of noise, and then you just regress them against the total signal and subtract them, and then you get your residuals and do your analysis on that. So people often, again, this is like different from lab to lab, but people will often use the motion parameters. They'll use ventricles and white matter. Ventricles contain information, a lot of information that's physiological about the heartbeat and respiration. White matter similarly does as well, although we do know that there is some bold signal in the white matter. It's just a lot smaller in amplitude to what you see in gray matter. People also use this step of bandpass filtering because they see that most of the power is below 0.1 hertz. In my own particular opinion, I don't think this makes a whole lot of sense, because the sampling rates we use are so slow that most of the artifacts we would sort of get rid of by doing this bandpass filtering step have already been aliased into the data range that we've got in the passband. So if you've got a 2-second TR, you can't measure anything faster than 0.25 hertz, and those signals are already now smeared below in our data range in a kind of unknown way, unless you're actually measuring the signals independently and then trying to make a model of that and extract it from the data with regression. People also commonly use the global signal. So the idea that it's definitely the case that if you just do these kinds of steps, you will have some residual artifacts in your data. The global signal has been much argued about whether or not it's a good idea to include it or not include it, what kinds of problems it might or might not cause. But it does empirically do a good job of getting rid of a lot of the more global artifacts. So you will do a good job with motion if you use it, and potentially breathing and things like that as well. Okay? So this is the $10 million question. How do we know if any of this stuff's actually working the way we want it to, right? We don't actually have a way. We have a way to look for artifacts. So we have measures of artifacts. We can measure things like the transient head motion present in a scan. So that's calculated by, taking the TR to TR change in the head motion parameters and finding moments where there's a really big change in head position, and just extracting kind of an analog signal from that. And it doesn't work very well directly as a nuisance regressor, but you can use it as if you average it over the scan, you can see nice dependencies at the group level for analyses. So it's one thing you can use, and that I'll show you a lot of evidence for in just a second, that you can see that there's still motion in the data. So we also can collect independent respiration and cardiac traces. I can tell you at NIH we almost all do that here. Lots of other places, though, they do not acquire these signals, so you really don't have access to them, and you really don't know if you have cardiac and respiratory signals in your data. Okay, so there are a couple of basic ideas here about what people have tried to do to look at this. So I really think a lot about the work of people like Ted Satterthwaite and Jonathan Power when looking for something like a motion artifact. And I'm going to show you some examples of that in a second. But what you can do is you can compare pre and post measures, or even just looking at post measures of cleaning, and look and see whether or not you can still see any evidence that these kinds of measures are still present in these data. Okay, so that's one way you can do it. You can look and see, I know I have a measure what I don't want. I can see if that stuff's gone. But what we still don't know then is how much other stuff's being taken out at the same time. We don't have a measure of that. For those of you, if you haven't seen this paper, it's Power et al. 2014 is sort of the most recent thing that they have done, sort of discussing They have a review after this, but there's a lot of good information in this about what happens in terms of the residual motion signals when you do various things. So let's look at a couple of those things. So transient head motions lead to corresponding changes in the bold signal. This is a subject who maybe doesn't move too much. They had this one event, so these are the actual motion parameters. This is this frame-wise displacement measure. That's the TR to TR change measure. You can see spikes here. And then you can see when you look at other measures, like this is the global signal, which is just averaged signal over the entire brain. You can see this same sort of corresponding fluctuations that seem to happen at the same time as the motion event. Now these are data that have not yet been cleaned. Okay, so you certainly expect to see that there. And subjects who have more of this, they have more motion, tend to have more of these kinds of events in their data. So there ends up being a very nice sort of relationship that you can see in a scatter plot if you just plot correlation between two ROIs or some other kind of measure like that, and then plot it against the average frame displacement. So this is another way that Jonathan Powell certainly has advocated looking at the data, but this is a bunch of gray matter voxels sort of strung out down on the kind of a y-axis here. These are white matter voxels, and then I think this is probably CSF compartment or something like that. But what you can see is when there's a big motion event, you can see this kind of brain-wide signal there. And in some of these cases, you see this sort of, this thing that seems later, right? So here's the event, boom, and then there's stuff that's sort of a long carryover. What we, I think, know a little bit more about this now is that this isn't necessarily motion per se, but somebody took a deep breath here. And when they did that, they had a breath withhold that then changed the bold signal everywhere throughout the brain. So motion is not just a thing in and of itself. It's often related to respiration. And so anyway, in any case, you can see the pretty strong dependencies of when these things happen, in measures you can still see that they're there. So Power et al. Sort of looked at a lot of different variants of these things, but the one on the left is basically the same model as the one on the right in terms of the nuisance regression approach. The only thing that's different is that the global signal has been included on the left. Let me orient you for those of you who are not used to looking at these plots. So in each one of these scatter plots, on the y-axis is, after cleaning, this is the correlation with frame-wise displacement. Okay, so if you see values that move off in this direction, it means that there's, between two ROIs that you pick, it means that there is a correlation in the sort of resting state value, resting state functional connectivity values, and frame-wise displacement. So any point in these scatter plots is the functional connectivity value for a particular subject and a particular choice of two ROIs. And along the x-axis is the distance in Euclidean space between those ROIs. So there are things here that are more nearby each other, and then things here are very far apart. So if you don't use global signal, what you can see is that there is a big, nice residual correlation with frame-wise displacement after you've done the cleaning in your data. And that value might be in the ballpark here, and the mean is maybe 0.25 or something like that. Now, what's going on with these conditions? So this has to do with whether or not you censor high motion time points or not. And this reprocess thing is a sort of a strange thing that comes up if you do iterative cleaning with censoring frames. But just comparing these two things, this is basically, do you cut the TRs out that have high motion going on in them and then just sort of splice the rest of this stuff back together and look at the signal then, or do you leave it untouched? And if you leave it untouched, even if you cut those time points out, you can still see pretty big residual correlations. Now, if you look over on this side, if you've included the global signal, it seems to do a pretty good job of getting rid of that dependency, okay? And this is just some statistical comparison showing this. So what's been advocated by these researchers is basically that if you want to get rid of motion, you want to censor high motion TRs and you want to do global signal regression. That is their argument. Okay, so the thing I mentioned before, though, is that people have been arguing that one of the things we want to really try to do here is make sure that we have reliable signals. What does that mean? If we take two scans and pick, we want to pick a pipeline that gives us the best test-retest reliability. So we're going to have two scans from a given subject. We're going to see, say we calculate resting state correlations in each run, and then we're going to see how much the same are those. The underlying assumption is that if you've removed noise, then the only thing that really should repeat is stuff that's real. Okay, now that's a little bit of a loaded assumption already because we know that some of the noise can be repeatable. So if people who tend to move their head a certain amount, if they move a lot on run 1, they're also probably likely going to move a lot on run 2. So it's not as clean as you'd like to sort of do this, but this is still something that is an important constraint. So let me just go through the basic thing that we know from statistics. So the agreement across repeated measurements, this is just the definition of test-retest reliability, taken by a single person or instrument on the same item under the same conditions and in a short period of time. The big constraint is that a test or measure can really not be more correlated with a different measure than it can be with itself. So if you're only correlated with yourself maybe 0.6, you couldn't possibly be correlated really with something other than that. Right? I mean, that it's a bound on what you can measure experimentally. Okay, so the reliability of our fMRI bold fluctuations and behavioral measures serve as an upper limit on what we're going to be able to measure in any kind of brain-behavior relationship. So what the stuff we really want to measure, if we don't have good test-retest reliability, that's going to be bad. We're not going to be able to do a lot. So Mike Millam has, for several years, been pushing on this point. So, and it sort of fits in the context of the larger discussion on reproducibility in neuroscience, where people want to be able to see the same thing over and over again, because believe it or not, that often doesn't happen if you actually set out to try to show that. So there's been a lot of different papers that are on variants of this, and I don't disagree with this. We have to have reliability. Reliability is not bad. That's good. You want reliability. So people have gone from, I don't know what just happened there, but okay, good. People have gone from just saying we need more reliable data also than to using this as a guide really to choose which pipeline we want to use, right? So if more test-retest reliability is good, we should make it as good as we can. So let's go into this just for a second. This is the Shire et al. Paper. So from what I've found so far, this seems to be one of the better papers that's really gone into some detail looking at which steps in a nuisance regression do and do not hurt or help test-retest reliability. So it's a good thing to start this kind of discussion. Okay, so this is a really complicated figure. So they looked at a whole bunch of different kinds of aspects of the So this particular slide is about bandpass filtering. Ignore everything on the right for a second. We're really just going to talk about the stuff that's on the left. So you can measure functional connectivity either between ROIs, which is the stuff in this column, or you can use it in dual regression with ICA, which is what is in this column. So they actually looked at both of these things. And then along the x-axis, they have different pass bands for the data. So they're going to try to filter the data. The thing that obviously seems to do the best, so I'm going to tell you what are on the y-axis now. But across a bunch of measures, almost not bandpassing at all seems to be the best, if this counts as best. So this is a high-pass filter starting at 0.01 hertz, so including anything above that. So if you look at the typical bandpass filter, it's actually not as good as doing less filtering. So along these, we have several different measures. This is actually test-retest reliability, and it's using the intraclass coefficient for reliability, the ICC, which is the preferred measure of test-retest reliability for a lot of different measures and different kinds of measurements. This is one they defined for this paper. It's kind of like a signal-to-noise ratio measure. It's kind of interesting. So what you do is you take within the big large-scale networks that people see, you look at sort of the average within network correlations, and then you also from those same spots calculate correlations outside the head, and you take a ratio of those two things. And so it's kind of like contrast to noise ratio, really, what people use for MP ranges, but it's done with these correlation measures for resting state. And this gives you some kind of measure of selectivity in a certain sort of way for correlations within network versus stuff that should be spurious. So that's what bandpass filtering does. We have things like white matter, CSF regression, and I'm not going to talk about CompCore, although if anybody's interested in that, I can tell you a little bit about that later. So there's a lot of these things. They don't seem to change these measures very much. They're, for some, the different bars and lines in these are actually different data sets, so you can see how well it does the same thing across a bunch of different data sets. In one data set, there's a change in the sensitivity. In one data set, there is an increase in test-retest reliability if you don't versus if you do use white matter. So on and so forth. One thing I noticed, just as an aside for those of you who know Carl Friston's complicated Volterra regression model, is that his tend to decrease the test-retest reliability, at least measured this way. So that doesn't actually seem to be helping, at least with regard to this measure. So these are more the sort of standard movement parameters, and you can see I mean, maybe there's a little bit of a difference, but it's not a lot. So one measure that we were just talking about, the global signal, it does seem to increase this sort of sensitivity or selectivity measure, whereas maybe it decreases a little bit in test-retest reliability. So this other sort of row down here is looking at classification accuracy. For this is comparing controls to Alzheimer's patients, and this is two different cognitive contexts within control subjects. So it's a rest versus a memory condition. So not much influence, at least for these data, on those contrasts. All right, so let's get to the main meat of this. This is sort of the study that we've set up based on these kinds of observations. If test-retest reliability is a good indicator of which cleaning procedures best remove noise and then spare neurogenic signals of interest, then measures of validity should follow the same pattern, right? If we could actually measure validity, that's really what we want. And I'm going to show you that I think we can define a measure in particular contexts of validity. So validity in this context refers to the extent to which we can use fMRI fluctuations or covariation to predict an independent behavioral measure that indexes the ability of interest for what we're looking at. So let's look at a few examples just to sort of get this idea clearer. And these are not, I mean, there's a bunch of examples of these. Actually, Emily Fenn, who's sitting right there, has another nice set of examples using behavioral measures and showing behavioral correlates using resting state networks. This one is very concrete. It is doing a set of localizers for faces and other categories of objects, and then looking at the resting state correlations among the face processing networks to say, hey, does this actually predict face processing ability? That's what they set out to do in that study. I'll show you that example in a second. We did another one where we looked at lateralization of function in resting state, where the contrast we made about what was lateralized was just made entirely from the MRI data. But then we found locations that seemed to correspond to language and visuospatial networks, and then we took the resting state correlations in those areas and showed you could predict language and visuospatial ability measured behaviorally. There are many, many examples. In fact, for the clinicians were in this earlier than anybody else, I would say, comparing clinical and control groups in resting state and then using the areas that show a difference with controls to try to predict the clinical symptoms in the patients. So this will help, I think, sort of cement what I'm trying to talk about here. We have a patient group and a control group, and we're comparing the means of the two groups. Okay, so we're going to select on that. That doesn't tell us anything about the rank ordering of the subjects within either of those groups. But then what we're going to try to predict in those areas is the rank ordering of the patients with an independently required behavioral measure. That's what we're going to try to look at. And if there is good validity, we should be able to see that it's the same areas showing the differences with controls as it is that show the correlation with symptoms. So this is just this example with face processing, just to get more of a concrete feel for it. So this group presented a bunch of different kinds of tasks with faces. They also had tasks with simpler visual objects as well as other kind of complex visual displays. And they did your kind of standard localizer to get the FFA and the PPA and the OFA and so on and so forth. And then what they found is if you look within the face selective regions and just take the localizer maps and then you just apply that to their resting state data, you can see that for face measures like face recognition, looking at a measure of the inversion effect in face perception and whole part effect, all of those actually showed correlation with the resting state correlations, whereas performance on other non-face objects did not show a relationship. Okay, so this is exactly what you'd like to see if this measure really is telling you about the processing of faces. So this is an example from our lab, and I'll just walk you through a little bit because we're going to get into a little bit of the using this to look at validity part too, in terms of testing different pipelines against each other. All right, so we published this several years ago on a study of autism, and it's not important for our purposes today exactly how we got to this point, but suffice to say that there's a bunch of different regions that we found that were different between autism and control. And what we did is we sort of organized them by their similarity into clusters. And so we've arranged that these are correlation matrices of regions by regions. So it's all with all. And so you can arrange the regions in this kind of cluster pattern. And then what we found is that the biggest differences in resting state between autism and control were this sort of between cluster relationships, whereas between ROIs in cluster 1 and those in clusters 2 and 3. But not so much difference among clusters 2 and 3. And when we do a t-test amongst these, this is where the biggest differences go. So before we look at the next slide, what you expect to see really is, well, what we hope is that these region combinations will be the ones that actually correlate with the level of social impairment that the autistic subjects show, for example. And that is exactly what we saw. So if you just extract for each subject the median value of correlation amongst these region combinations, they are in fact correlated with the social responsiveness scale. Now, this scale is a measure of social functioning that's found by a survey with the parents. So it's not even just that we're not measuring it at the same time. It's not even really, it's a report not even by the subjects themselves, it's by their parents. All right, so these were the region combinations that also showed correlations with the behavior of interest. So one of the things we noticed when we were doing that study, because that was sort of our first big foray into resting state, is we tried pre-processing a bunch of different ways, and we noticed that not all of those ways gave you the same answer. We noticed in particular that the global signal seemed to change things a lot, at least for this data set. So I have this arranged in that same cluster order. So here's cluster 1 and clusters 2 and 3, and these are the t-tests between groups. And so I'll just walk you through what these different so it's not all possible nuisance regressions, obviously, it's particular ones. So this is what a lot of people would use if they don't use global signal regression. It's basically the motion parameters, measures from the ventricles, measures from white matter, and but then not using global signal, right? And then the global signal is that same pipeline, except now we've added global signal to the mix. This is the same as this model, except we've added a group level covariate, which is the grand average correlation of all voxels with all voxels. So this is a different way of getting at a global level of correlation, kind of a global artifact that doesn't work the same way as global signal regression does, because it's done sort of at the group level, and it's doing it essentially adjusting the t-tests for that nuisance covariate. So this is the original results that we had. So this is our anati core pipeline, which basically is the same as what I just told you, except now we've added some physiological measures too. We've added retro core, which contains the heart, the cardiac cycle measures, as well as the respiration cycles that have been aliased. We have the estimate of what their aliasing is using Gary Glover's retro core. And then we also have this thing that Rasmus Byrne came up with, which is a much slower evoked response of respiration, called respiration volume per time, which is really related to the sort of PCO2 effects that happen when you have a big breath withhold. So when we added those, this is when we found our nice correspondence between our group differences and our behavioral correlations. Notice that the behavioral correlations don't ever really look as nice under any of the other pipelines, at least using these same ROIs. The group test can kind of look the same, so you can see this for this what we call the basic model versus the G-core. That actually looks pretty similar, so we can get kind of the same results if we do that. But global signal regression is really strongly altered, and there's really no relationship between these measures and these measures amongst these ROIs. And the only one that really does show a significant relationship, if you permute the data to get a good estimate. It's hard to get a statistic of how similar a matrix is with a matrix because of all the row and column dependencies. So permutation is really what you have to do with row and column shuffling. And so this is really the only method that we've seen, at least for these kind of studies so far, that actually gives us nice validity. All right. So what we thought we would do, so there's still a lot of debate and arguing about this. There's still people saying, no, we have to do global signal regression. We say, don't do global signal regression. That's a bad idea. And how are we going to get past this? What should we do? So the idea, there are also other new ideas about how to clean the data that seem like they were interesting that we should try as well. So Peter Bandatini's group here developed this sort of MICA or multi-echo ICA approach that we thought would be interesting to try out. So in the process of a different study that we're trying to look at repetition priming and recognition memory, and that's the study that Adrian and Sarah and I are all doing together. What we did is we took the first 2 runs. So that's just, we're naming pictures. So this is a task where we got 2 runs where people name pictures. That's it. So we're going to utilize a phenomenon that's been seen when people do tasks and measure response time to try to get a measure of validity in a task-based setting. Now, so this is not rest, RO. This is not resting state. This is now a task-based study. However, the artifacts, the considerations are really exactly the same. Our main signal of interest is using fluctuations in the time series. We are looking trial to trial, single trials, and trying to predict response time from the bold response. So if I have motion in there or cardiac or respiration, that's going to influence all these measures and make them worse. So we're going to use this phenomenon that's been seen many times before us, where we're going to look at the relationship between the peak bold response on a trial and its response time. Okay? So here's a little example to give you a sense of this. So this is a study by Rao et al. And what they did is, it's a pretty complicated task. They had subjects do this as fast as they could. They gave them basically a list of these symbols and a key, and they had to, as fast as they could, type in the right number and indicate which one matched which symbol. So you got to keep going back and match this, sort of abstract symbol and do it as quickly as you can. So they measured the overall task response doing this task, right? And that's the task positive stuff is shown here in the sort of gold, and then in the lighter blue, that's task negative stuff. That means that the response went below the baseline after the stimulus onset. So what they found was that there's a positive correlation, which is what others have seen before, between the magnitude of the bold response and RT. Now what that means is the higher the bold response, the slower the response time, the bigger or longer the response time. So that's the thing that's typically seen. So we're going to use this form of a behavioral measure, and we're going to do this in a slow event-related design. Okay, so a slow event-related design differs from a rapid event. Usually with rapid event-related, you just want to get the mean response for a condition. So you're going to randomly intermix things. You're going to have baselines randomly intermixed of different lengths. Some things will happen when one trial comes right after another, and then you'll, another time maybe wait a long time. With this, you have something that's a little bit more periodic, and you don't have baselines that are separate. So we have jitter, and we'll have a trial every maybe 6 or 7 seconds, ranging up to every 12 or 13 seconds. So there's a range, and the average is somewhere about 9 seconds or so. But what it'll allow us to do is that the peaks of each trial will not be overlapping across the trials. So we'll be able to separate those, and then be able to look cleanly at our measure of, what is the bold response in this voxel on this trial, and then our response time that we measure. So it's overt picture naming. We're actually having subjects move their jaw during this scan. They see a picture of a tiger or a car, and they just have to say tiger or car as quickly and as accurately as they can. So we have in this, what I'm going to show you today, we actually will end up having 40 subjects, but this is the first 20 that I analyzed. For these, they named 100 pictures that were spread across 2 runs, 50 in each run. Now these are not the same items. So they're different. They're all novel for this sort of experiment. The subjects haven't seen these particular stimuli before. They get 50 of them in each run. What I do expect to be the same for something like a test-retest measure is I expect them to show beta weights in the same places. I also would expect any kind of pattern of task-based functional connectivity to look pretty much the same across the 2 runs. So those are going to be our 2 measures of test-retest. As across run 1 and run 2, I expect those to be about the same. All right, so we're going to record response time and accuracy by recording the voice responses. We have a noise-canceling MRI-compatible microphone, And so when we're there in the booth, we hear the subject and we can hear the naming responses. Sarah sits there; she's listening to the response. Is it correct? Is it not correct? And then we can process them afterwards. When we have a marker of when the trial starts, we can see when was the onset response to the voice energy, and we can mark the response time. So this task, we're using a multi-echo MRI design. So for those of you now, Javier's talk on this is not going to be till later. And usually I give this talk later in the MRI course, so there's a context where everybody's had all this kind of stuff. So if you don't know what I'm talking about, please stop me, and I have time. I'm not pushed on time today. I can go into the details if you need to know. But what you're going to get with this paradigm is in every TR, and the TR here is 2.2 seconds, you're going to fully read out the entire brain volume 3 times. So one at a TE of 12.5 milliseconds, another at 27.7. Now this one is very close to T2 star contrast that we would normally use for bold. So we can compare single echo and multi-echo just by notching out this one echo time readout. And then we also have a later TE at 42 milliseconds. I'm not going to go into a lot of the details of exactly how this works. What I'll tell you right now is that when you do ICA across these 3 readouts, components that really are reflecting the bold response should change linearly over the readouts. And so that's actually the measure, is you get these parameter fits about, all right, how linearly across 3 readouts is this component changing? And if it's really linear, it goes in one pile. If it's really not linear at all, and a straight line is a poor fit to those 3 points, it goes in the other bin. And then you reassemble the time series with the good components. Okay, so that's essentially the simple version of how this works. So what you're really trying to find is not a particular pattern in space of where networks are. It's literally, does it follow what we predict from the bold response or not? That's it. So it could have whatever pattern in space that has. Okay, so as I mentioned before, how are we measuring test-retest reliability? So we're going to have 2 runs. We calculate beta weight separately on runs 1 and run 2. We can then compare how similar those are over the whole brain. We also can get a voxel-wise measure of task-based functional connectivity. So in run 1 versus, so let me tell you how I do this. So I didn't want to do a parcellation necessarily because I don't think we need to do that for this. So I literally just downsampled the voxels to giant voxels. I think I used 8 millimeter voxels here. And then the matrix of 8,000 voxels in the EPI volume was like about 5,000 voxels or something. So I can do it easily for each subject, a 5,000 by 5,000 matrix without running out of memory on my desktop. And then I can just see, all right, is the pattern of correlation in that giant ROI to ROI correlation matrix, to what extent is it the same across the 2 runs? So this is going to contain more information about fluctuations happening trial to trial, right? So if you had a big outlier trial on one run, then you might have a big spike on that trial, and then that might really change the correlation coefficients in that run, making them not the same in run 2, right? So you can also imagine how that could screw up the beta weights as well if you didn't have enough samples of the trials. So let's say I only had like 10 trials and one of them was a really big outlier, then my beta weight estimate probably isn't very good on run 1 versus run 2, right? So they could be reflecting similar things, but if I expect anything to track the RT correlations, ahead of time I would predict it would be this one. Okay, so how are we going to get at validity? We are going to threshold. So this is kind of like thresholding on the group response and then looking for the symptoms within one group. It's a little bit like that idea. We select voxels from the beta weights. So it's actually on the significance of the beta weight. And this is pooling the 2 runs now. So we will find out, all right, well, where are the best stimulus responses that I get? So this is just literally taking the TRs between, so like the third and it's the second and third TR, or the third and the fourth TR, right at where the peak of the bold rise is, and we just average it. So for each voxel, that's the trial's bold response. We've done a t-test on that across subjects versus 0. So this is just within subject. This is based on the general linear model. So we can either take the top 1,000 voxels in that map, we can take the top 2,000, and so forth. And this way, even if the significance isn't the same across pipelines that we're going to look at, it doesn't matter because I'm going to be looking at the same number of voxels for each comparison. So each one has an equal chance to get to contribute. All right, so we're going to threshold at different levels of the stimulus response, and then we are going to try to, within those, predict response time. And that's done voxel-wise here. So you'll get a correlation in each individual voxel, and then you're just going to average them within the top 1,000 or average them within the top 10,000. We also have a condition where we just use a whole brain mask to look at how correlated on average over the whole brain. So you can get some sense of how selective, if we raise this threshold, does it improve the validity or not, right? So we're going to ask which preprocessing pipeline now gives the best validity, and does this agree with which one gives you the best test-retest reliability? Okay, so it's not super important right now to follow all the details of what I'm doing here. One of these is going to be the MICA pipeline. One of them is optimally combining the echoes across those 3 readouts, which has no cleaning really. It's just trying to assemble what you would have kind of like a single echo image. But it's trying to optimize across the 3 echoes to be T2 star. We also have this starting with number 2 here. We also have tried nuisance regressions, right? So we've added the motion parameters, the ventricles, and white matter and global signal, or we've done all of that without the global signal. We've also done our natty core pipeline that, in addition to these, elements, also includes retro I-core and RVT. And then we've got single echo pipelines from the second echo, right? So we can do a couple of things. We can see, all right, well, is it worth it doing multi-echo compared to single echo? Does that help? One of the things that happens when you combine across the echoes here is you actually dramatically reduce thermal noise, which is a big part of the signal at 3 Tesla, because you've essentially averaged the images over the 3 readouts. So instead of averaging in space, so spatially blurring to some extent to get rid of thermal noise, this averages in time instead, but you still aren't losing your temporal resolution because you still have 1 measure per TR. So you're going to expect to get a big boost by removing thermal noise for optimally combined. So we can look at what the impact of not having any blurring on a single echo is. What happens if we then just add blurring? So there hasn't been any nuisance regression. It's just essentially pretty raw. Now, one thing I should say on all the pipelines is that they've all, because this is a GE scanner. Oops, I must have clicked it. Because this is a GE scanner, we had to cut off the first few TRs for the magnetization artifact. Then the images are despiked, which is a voxel-wise kind of operation where we get rid of any outlying time points that are greater than 4 standard deviations, and they squash them to within 4 standard deviations. We then correct for the slice time acquisition, as well as volume register of the images. So even this has had all those things done, okay? And so these are all just additional things that are done after that. But then we can have these are what people would typically use in data that we normally would acquire now. So you would have, after you blur, you've got your nuisance regression with motion parameters, ventricles, white matter, and global signal, or you do it without global signal, or we have our natty core pipeline. So this would be what we've done in previous studies multiple times, okay, that we've used number 5, all right? Okay, just for those of you who have not seen this kind of thing with multi-echo, here's what the they're not really bold images, but this is what the reconstructed EPI images look like at the different echoes. So you can see that different tissues have different decay times across the readouts, and this one in the middle is what we would typically use for our normal sort of typical bold scan when you're just doing single echo. So it's across these 3 readouts we're looking, but this is going to be the echo that we take out. So just so you get a more concrete feel for what we're actually doing on an individual subject, this is beta weights, right? So this is just the stimulus response versus 0. And if you see anything red, that means that the bold response was greater than 0 when the picture came on and the subject named it. If you see anything blue, that means that there's actually a task negative response in that location and it went below baseline. So if we threshold in the top voxels, this is the, for this particular individual subject, this is the correlation of response time with the peak bold response. So I thresholded it at 0.05, but there are some FDR corrected results here, but everything I'm showing is just uncorrected, so you can get a sense of where everything is in an unthresholded map. Or it's still thresholded, but it's very liberal. So you can see already, see this overlap here in the frontal cortex, as well as in the occipital cortex and the thalamus. You get some overlap with these. So to the extent that these maps are the same, then this is going to show good validity, right? That's the bottom line. But this is going to be the map that is thresholded that then will be applied to this map. Okay, so here are the results. So let me just walk you through how I'm showing this. Each one is showing almost like a little tuning curve for validity, all right? That's how I've kind of set this up. So each little column here is a different pipeline. Along the y-axis is literally just the raw voxel-wise average correlation with response time and the peak-bold response. So you see it's not super large, right? I mean, that's just, on average maybe 0.11 at the best. But if you look at a group level effect where every individual subject is about like this, that's an awesome map. And so I've looked at this at the group level, and it's great. It's actually good for pretty much all of these except for a couple. Okay, so you get significant validity for virtually all the pipelines, at some of these thresholds. So then what I'm showing is within one of these curves, the farthest left point is the top 1,000 voxels. And then moving on down, it goes 1,000, 2,000, 3,000, 4,000, 5,000. The final point is 10,000, and then this drops down to a whole brain mask. Okay, so if you use the whole brain mask, that's the average voxel-wise correlation. So you can see that when I threshold up the stimulus response map, it does improve the validity, right? And that's significant, for each pipeline. Okay, so few things to notice. All right. So all of the pipelines give some significant validity in the sense that they're different from zero for everything except this one with global signal and the optimally combined data. That one doesn't have any points that are different than zero. Even this Echo 2 does better than that. The first few points do not differ from zero, at least at 20 subjects. But then by these sort of later thresholds, they do. Okay, so the other thing to notice is that so far, multi-echo ICA is by far really the best. It's doing better than all of the pipelines, significantly so. So that's an interesting, we started out not knowing what would happen, and I bet that we'd be doing pretty good with our pipeline here. This is ours over here, that we'd be doing pretty well. So the other thing that's a little distressing. Well, let me mention this point first before the really distressing part. So the two GSR pipelines are the two worst. They don't do as well. It's an open question for me at this point whether or not this is really going to be exactly the same when we do the resting state analysis, which we're also going to do for this study. So we have resting state data for all these subjects, and we do have a behavioral correlate that we can use from this task that we can look at in resting state that shows a correlation. So we're going to look at that. There are different this is all within subject, these measures. So if I add a terrible trial in, it probably on the sum of it over 100 trials is not going to be that bad in terms of me doing my analysis. But if I have a big couple of spikes in there, and what I'm using is instead the overall average correlation between two ROIs, that's going to give a big spike to that. And if that's the only measure I have, that's going to be a problem potentially, whereas this within subject measure within a scan maybe wouldn't be a problem. So these different kinds of analyses for validity may not show the same thing. We're going to find out what happens when we do that next set of analyses. All right, so the next point though, and this is the more distressing point, is that doing nothing is better than doing something. So in terms of the validity, you actually contain more information about behavior by not doing nuisance regression. In other words, by not taking out the stuff that's head motion that we know is in there, and by not doing the best we can with cleaning the data in the way that we've always cleaned it. So even just look at this, the Echo 2. This is literally, I've just done basically a task-based pre-processing for this and nothing else. It's got thermal noise in it. Every voxel has thermal noise, right? And it actually does really pretty well. All things considering. You can see there is a benefit from going to this unblurred sort of single voxel measure in Echo 2 up to the optimally combined data. So that's nice and significant. There is a boost if we go to the sort of the blurring, right? So if we spatially blur and get rid of some thermal noise, that helps with this a little bit. And it takes it almost to the level that the optimally combined is. But anything after that makes it worse. Right? So what's going on there? Well, the things that we have to check, we have to decompose some of these pipelines and see which elements are the worst and are really the biggest culprits. Is it the white matter that's doing this? Is it the ventricles that's doing this? I mean, I can see how the white matter could be. because that does have bold signal in it. But at this point, it's not clear. The main thing to notice is that it's not actually helping in terms of this validity measure and correlating with behavior. We have also done, now another question you could ask is, well, how do you know this isn't just motion? Something like that, because that's going to get asked. I have done several things to check trial to trial if there are fluctuations that might covary and have a third variable mediating them with response time. So we have response time, but what if motion drives both response time variation and the peak bold response? So we have looked at that by getting a trial-specific measure of frame displacement, and we've regressed that out here. And I haven't done that for these more recent data. I did them for the first 10 subjects, and it didn't change anything at all. Although, interestingly to note, the pipeline with the least dependence on motion was the global signal pipelines. So, it did actually do what it has historically done, which is to remove motion well. But the other thing that you can do is that you can really sort of take this to the extreme and say, well, what else could I remove from this really to guard against other kinds of things that might still be in there that I don't know about, right? What could I take? You can actually take the global signal itself and covary its shared variance with RT and the voxel-wise bold response and remove that, and it doesn't change these results pretty much at all. And the reason behind that is that it's not well correlated with response time. So it has to actually be correlated with all the variables in order for it to get removed when you do that partial correlation. And because it's really not related systematically to response time, it really doesn't change this very much. So all of these results still hold if you covary that out. So I don't think that that's the reason. I don't think it's this other explanation, that there's some global artifact that's residual in the data. I think it actually is. This is a reasonable measure of validity, at least for this context. Okay, so test-retest reliability, which we haven't looked at yet, right? Here are the results. This is not the interclass coefficient, and I will do that next probably. It's probably a more proper measure of test, but this is a very concrete, intuitive one. It's literally just, you can square this and get R squared, right? So you can say how similar are these two maps that I'm comparing. And the dark bars are the whole brain test-retest correlation with the beta weights. Even the voxels that are not stimulus responsive and so on, it's literally across the whole brain. The lighter bars are the sort of the measure of task-based functional connectivity. You can see that these values are actually not terrible. They're in the ballpark of 0.6, maybe even 0.7 for some of the measures, based on about 9 minutes. So that's kind of in line with what we'd expect, I think, from all the analyses people have done of resting state data in terms of what the test-retest measures are. And these are put in the same order. But the interesting thing about this is that the most reliable measures are the ones that are single echo and that have blurring. And those are not the same as what I just showed you before. So the multi-echo ICA pipeline is not particularly large in its test-retest reliability for any of the measures. You can see that for the porous validity, there is a little dip here for the global signal pipelines, although not as much for the single echo ones. So for example, the test-retest reliability for the global signal pipeline for single echo is greater than it is for the just echo 2, but the validity goes the other way, right? Okay, so of these two measures, though, the beta weights and the task-based functional connectivity are intercorrelated with each other, so they do capture some of the same stuff. Neither measure, however, is related to the best validity measure. So what you can do is literally for each subject that has a certain pre-processing pipeline and a certain scan, you get a measure of test-retest reliability, and you also have a measure of validity for that. And so there's a whole bunch of data points here, and you can just say, hey, do these numbers relate to each other or not? And I'll show you the scatter plots in just a second. So on the left, this is the top 1,000 voxels. This is all the different scans that contributed to this. And then this is the task-based functional connectivity test-retest reliability. So this is a big football, right? This is not significant. There is a significant correlation if I threshold this down a little bit. So if I now, instead of the very best voxels that give me validity, I threshold it down a little bit and take the top 10,000, which is a lot more brain at 3 millimeter voxels. then there is a modest relationship. You can see it's 0.27. That's certainly not very inspiring if you want to use that measure as the main measure for getting the best validity results in your study, though. So it's not that they're not related at all, but they're pretty weakly related, is I think the bottom line. So neither measure is really related to the best validity voxels. Those are really small correlations. And only the only measure that really is related in any situation is the task-based functional connectivity measure, and it's not that strong. Okay, so let me just summarize briefly, and then we can go into some questions. So thus far, MICA appears to perform the best, at least for this particular measure of validity. Obviously, we need a lot more studies and a lot more measures of validity, because the reason people probably haven't done as much validity studies before, is that it's hard if you just have a bunch of resting state scans. What are you going to measure? That's the function you really want to measure. I mean, it's not impossible. People do it. I've showed you a bunch of examples where people do it. But it's just been done much less. It's easier if you have 2 scans to do test-retest reliability and just do that. You don't really have to think about which domain you're talking about and what problems with those measures there might be as much. And it's just a quick thing you can get. But the nature of validity is that it's pretty tied to the thing you're studying. So we need to look at a lot of different things, I think, before we can be sure that you get the same answer over and over again for the different pipelines. Okay, so while test-retest reliability provides an upper bound on the level of validity, and I don't dispute that at all, certain procedures seem to have a pronounced effect on validity that really don't appear to be reflected directly in the reliability measures. So it's not going to be easy to use those reliability measures to choose which pipeline if what we really want to maximize is looking at a particular brain-behavior relationship. So the preliminary results indicate that most of the nuisance regression approaches are actually removing signals of interest. So that's my bet at this point as to why the validity measures are dropping when we look at the nuisance regressions. I can give you anecdotal examples throughout the years as to the same kind of thing happening where we've been trying to do something like, all right, let's present a bunch of words and use multivoxel pattern analysis and try to classify which word I'm having subjects look at. And we did this version of this study, and we decided, well, we've got all these physio measures. Now let's clean the data like we would for resting state and get rid of as much noise as possible and give ourselves the best chance. What we noticed was that the performance in doing that classification with individual words was really hit badly by doing the nuisance regression, and we didn't really know what to make of it at the time. And in retrospect, it seems kind of consistent with what we're seeing here, that it's potentially that because we can't measure the signal of interest, we don't know what it looks like, and as a result, when we're doing our nuisance regressions, we just don't know how much collinearity there is with those signals and the nuisance measures. So that's my current interpretation. As I mentioned, we plan on repeating these same analyses in a more across-subject analysis with resting state data. I can tell you that so far, I've looked at the MICA data, and there is a nice big correlation with median response time across subjects and the average functional resting state connectivity measures that I think we'll be able to use. So it's even correlated in the grand average correlation across the brain. So if I just take a single number from each subject, which is the average level of correlation, it is correlated below 0.01 with the median response time. And centrality measures show really big, robust FDR-corrected results so far. So I have every reason to believe I'm going to be able to look at these kinds of analyses as well with all of these pipelines and see which ones, see if they translate to that different kind of cross-subject analysis. Okay, that's what I have. Okay, Valentinos.
So your hypothesis that you're removing signal of interest, but let's say an article. But that's easy to test. You have a block design, you can see the blocks. It's very hard to figure out why would that be, for example, if you are replacing things from the middle of the ventricle, so like leaving white matter.
I agree. I don't. So the question that Valentinos asks is, it's hard to see. Let me just restate it. So if we do task-based analyses, we don't get effects there, right?
You don't see the, yeah, you don't see.
Right.
You know what to expect.
Yeah. That's so. Why is it that we're seeing that here? Right, so I think that's a good question. Although when people have carefully tried to measure bold response in white matter, you can actually see little evoked responses in the white matter if you have enough power. So,
Depending on how much you erode.
Yeah. Well, there's the partial volume effect with gray matter, which is a different issue. But that's, yeah.
I'm trying to hint at another possibility that it might be that you have reaction time prediction in your noise variable. Instead of regressing signal, you have predictable effects in reaction time in the analytic core covariance. Like what if you vary the analytic core signal that you use for light matter dimensional with reaction time to see how much?
Well, we can certainly look at that. We can certainly look at that. I mean, that's been removed, though, right? So you think that the third variable is that, so there it is possible. So this example gets brought up a lot in clinical settings. Let's say there's another measure, like motion or whatever you want to have, that for whatever reason happens to be collinear, right? Let's say that people who are most autistic, doesn't have anything to do with this, but let's say they also move a lot, right? Let's say that there's something that's an underlying third variable that's driving that, and as a result, it just happens that if we remove this, it's going to remove that too, right? It's possible. I think, obviously, if we look at a whole bunch of other kinds of measures, and that still keeps being the case. So I think it'll be instructive when we look at the correlation in resting state, when we look at, sort of across subjects, and then I've got tons of clinical data in different disorders that, once we start to get to a certain number of variables that we see the same thing happen with, then it might start to be less possible that sort of collinearity is really what you're seeing. But but what it would have to be non-bold though, right? Like for the mica stuff, what's the explanation for that, right? Because if we do the covariate with,
well, that's really bizarre. That's correct, but you get the same voxels between, let's say, inadequate mica, or does mica, for example, focus?
There's a huge amount of overlap about where the correlations are. Yes.
I mean, sure, it should involve the
Yeah.
same, but let's say, does mica perhaps give you more task-based related regions, and it drops regions that are completely unrelated?
Well, there's nothing that's super gross like that, but yeah.
I would focus on regions where naming categories is significant, and around the validity test to see whether, because you wouldn't expect spurious results in them. They should really predict reaction. Just constrain the analysis in those regions and see how the different.
Well, so one thing that is the case is that if you look at these two maps at the group level, so I've done that. These are all individual subjects. Like we're using the individual subject's best 1,000 voxels or whatever for selecting which voxels we're going to look at. If you look at the group level of analysis and go into standard space and do that, if you look at the maps of which things respond above baseline versus which things are correlated with response time, they are not identical maps. They overlap a lot. There's a lot of places that overlap, but they're not identical. There are definitely regions that are more involved in one map than another map, where you get a contrast between them. In fact, I would say that on average, if you look at those maps for the behavioral correlations, they go up a lot relative to what we are seeing here with selecting on the stimulus responsive voxels. So what's the peak average, the mean across subjects in, say, the MICA pipeline? Like, what's the best group average level validity that you get? And the answer is like 0.24, 0.25, which is a lot bigger than 0.11. And it's just that the maps mismatch enough that when you select the top voxels for one, they don't happen to grab the best voxels for the other map. So there are different versions of this we can look at. Like we could take the first 20 subjects, take their validity map, and use that to constrain the second 20 subjects maps and see if things get boosted more, if any of these results change. We can certainly look at that. But yeah, no, we'll have to think more about the third variable problem and see if there's any I mean, it could turn out that it's really clear when we decompose these pipelines and one of them is really bad. Like one of them has a big impact and it'll make it clear what's going on. Mikhail. I think that is a fair point. I would not put words in Jonathan's mouth about that. So let me restate the question for the people who are going to watch this on the video later. So the question is, well, okay, so you found this for task, but you kind of transparently would expect this to happen for task because there's so much of the brain engaged by a task. It's definitely going to bleed into the global average. You're definitely going to subtract out stuff when you do something like global signal regression and make it be less. And there are a couple of things I can say to that, and that is that you might find yourself in an argument with people who don't agree with that statement. But I don't know that it will be the same. I did notice that if we look back at this validity plot, let's do that real quick. Here we go. This is the same rank ordering in this plot that we found in our previous Frontiers paper. So it's not, I mean, it's a little bit better here than it is here. It's a little bit better in these two than it is here, okay? That's not different. That's basically pretty comparable. In fact, so we're going to find out, though. We have the data. We will just do it and see whether or not it plays out the same way. Yeah. Well, the pipelines were not designed for rest, exactly. The pipelines were designed to remove certain noise sources. And those noise sources are in these data just as much as they are at rest data, right? So if I do a plot of motion and I do frame-wise displacement and I look at the correlation in task-based, functional connectivity, it's going to look almost exactly the same, right? And it does. I mean, I've looked at it. It's, so all those same factors play out almost to the same magnitude of extent that they do in rest. And since we're looking at a fluctuating signal, and that's our signal, the same argument applies that, well, if that noise source is in there and this gets rid of that noise source, I mean, it's not as if in those other nuisance regressions we're removing gray matter signal out, right? So why should that be worse, right? Okay, but I have gray matter. I'm not taking any of that out. It's all in there. Yeah. Yeah, none of the measures we've taken simultaneously, these kinds of things, those show much fit, though. So they really are not obviously, they're really not obviously explaining that. I mean, that's why it's a bit perplexing, right? There is not an obvious answer. I mean, I understand the obvious answer about the task-based driven signal for these things. I get that. That makes sense, right? But it doesn't make sense to me at all when, as Valentino said, there's really not a lot of obvious task contrast when I do my task contrast. I don't get a bunch of white matter ROIs, right? I mean, I don't see that when I do that. But nevertheless, there's something is shared. Obviously, that's just this restatement of the finding. But it's not obvious at this point what that is or why it should be that way. So. That was resting state.
So whatever happened here happened in the resting state.
An ADI-core is slightly better. Yeah. Yeah. No. That's sorry. I should point that out. This this little difference here, right? Because this is like the basic pipeline, right? I would have predicted ahead, and I did predict ahead of time. This Echo 2 would be terrible. I mean, it's got, it's a voxelized measure. It's got, a third of the signal is thermal noise, and I'm doing a correlation that should hurt it, right? So it's interesting that it's really it's so robust to that, and that it's really not changed much by doing the kind of covariates with global signal or doing motion measures. So.
Global signal is the one that will keep me up at night. The rest I can live with.
Anybody else? Okay.